Hey everybody. Today we're talking about the negative binomial distribution, which models the number of Bernoulli trials needed to obtain a fixed number of successes. We write NB of R comma P for that distribution, where R is the number of successes you're aiming for, and P is the probability of success on any given trial. By the way, the geometric distribution is just a special case of the negative binomial with R equals 1. Here's a picture of NB of 4, 0.4. So we're trying to get 4 successes with a probability of 40% on each try. X can't be less than 4. Obviously, you need at least 4 trials to get 4 successes. There's no upper bound on the number of trials you might need, but after a certain point, larger values become increasingly unlikely. Let's dig into this particular negative binomial distribution a little more closely, a little bit deeper, just to try and understand it a bit before we get into some of the more abstract math. For x equals 4, you have 4 trials. All 4 of them must be successes. You've gotten all 4 of your successes already. So the probability of that happening is just 0.4 to the 4th. 0.4 is the probability of an individual success. It's about 0.026. For x equals 5, you have to have exactly 1 failure, and it actually has to come in one of the first 4 trials, because the last trial has to be a success if that's where you stop. So I've listed the 4 possibilities here. They're things like n, y, 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 y. And each one has probability 0.6 times 0.4 to the 4th, because you have 1 failure and 4 successes in these independent trials. There's 4 ways then that can happen. All the probabilities are the same, so 4 times that. We get about 0.061. Finally here, let's look at x equals 6. And in this situation, in those first 5 trials, you have to have 2 failures and 3 successes. As before, the last trial has to be a success. I've only written down a few of the possibilities here. There are things like nn, y, 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 and yn, y, y, ny. In total, there's 5, choose 3 or 10 ways that this can happen. Again, you have 5 trials, excluding the last one, when x is 6, and of those, you have to have 3 successes, because the last one is going to be a success. The probability of each one of those is 0.6 squared times 0.4 to the 4th, so to get the overall probability that x equals 6, we do 10 times the thing I just said. It's about 0.092. By now, we're starting to see a pattern. The last trial is always a success, while all the failures and all but one of the successes have to come in the first x minus 1 trials. Overall, there's x minus 1, choose r minus 1 ways that can happen, and each one of those has a probability of p to the r, q to the x minus r, because you've got r successes and x minus r failures. So overall, the probability mass function for a random variable that has a negative binomial distribution is x minus 1, choose r minus 1, p to the r times q to the x minus r, where x can be r, r plus 1, r plus 2, etc. For instance, in this example where we have parameters r equals 4 and p equals 0.4, the probability mass function is x minus 1, choose 3, times 0.4 to the 4th, times 0.6 to the x minus 4, for x equals 4, 5, 6, 7, etc. We can compute individual probabilities just by plugging in the value that we're interested in. So the probability that x equals 8, for example, is f of 8. You can see I've plugged into this formula here and gotten about 0.116. There's an 11.6% chance that it takes exactly 8 tries to get 4 successes, when the probability of an individual success is 40%. Now, you have to be really careful when working with a negative binomial distribution, because some sources instead let the random variable represent the number of failures rather than the total number of trials before the rth success. And in that case, the probability mass function looks slightly different. I have it written here. I won't say too much about it. The advantage of that approach is that the support is always the same. It's the non-negative integers. You're counting the number of failures, so you could have no failures before you get all the successes. The downside of it is that it can be really awkward to count the number of failures rather than the total number of trials. Now, both formulations are in widespread use, so you really do have to be familiar with both of them. Fortunately, translating back and forth between the two isn't hard, because the total number of trials is equal to the total number of successes plus the total number of failures. So mathematically, y equals x minus r. Now, in this vid and others I do, I'm going to stick to the first one of these. I like talking about the total number of trials, even though it means I have to be careful with the support. For instance, suppose a child rolls a fair 6-sided die until they get their third 6. I'd like to know what the probability is that they need exactly 20 rolls and the probability that they need at most 20. So as usual, I recommend pausing the video here, trying this problem on your own before seeing my solution. First, let's do the probability of it taking exactly 20 rolls. We're in the negative binomial distribution with parameters r equals 3 successes needed, and probability p is 1/6. So you can see I've plugged in those values in that first line for f of x, and then to compute f of 20, the probability that x equals 20, we're also plugging in to the x equals 20 value. I do a little bit of arithmetic, I get 0.036. About a 3.6% chance that it takes the child exactly 20 rolls to get that third success. Now, it's possible to compute the probability that at most 20 rolls are needed just by plugging in directly, doing this individual probability mass function for the values from 3 up to 20, but that's a lot of work. There's an easier way because getting 3 successes in the first 20 trials is complementary to the event that there are no more than 2 successes in the first 20 trials. And we can compute that latter thing just with a binomial distribution. We're going to do 1 minus the probability that y is less than or equal to 2 when y has a binomial distribution with parameter 20, n equals 20, and p equals 1/6. So that only involves computing those 3 probabilities in a simpler binomial distribution. We do 0, 1, and 2. We do a little bit of arithmetic there. We get 0.671. And that connection between the binomial and negative binomial distributions is often helpful to you, so watch out for that. The name negative binomial actually comes from the fact that the coefficients of the distribution's probability mass function are the same as the coefficients of the Maclaurin series expansion for f of t equals 1 minus t to the negative r. I'm not going to say anything more about this here because I don't want to get into those dirty details too much, but that's the origin of that name. The mean variance and standard deviation of a random variable with a negative binomial distribution are shown here. The expected value is r over p, the variance is rq over p squared, and the standard deviation then is just the square root of the variance as usual. Here q is 1 minus p, that's standard notation, q being the probability of failure. I'm going to skip the proofs for now. They're based on the moment generating function, which we haven't covered yet in normal knowledge probability. For instance, in that example with the child rolling a die until they get 3 successes, the expected value, the expected number of rolls needed, is 3 over 1/6, 3 times 6, or 18. The variance, rq over p squared, 3 times 5/6 over 1/6 squared, 90, and the standard deviation, the square root of that, is 9.5. On average, 18 rolls are needed to obtain 3 sixes, and I think that makes sense. You have to get 3 successes, and you kind of expect that you're going to need 6 tries on each one because there's 6 possible rolls of that die. An average attempt will differ from this expected value by 9.5 rolls, very roughly speaking, so there's a fair amount of variability in that expectation that it's going to take you 18 rolls to get those 3 sixes.